Yeah, hi, good evening. So today is the lecture 6. First of all, so if I revise the topics, uh, so uh, okay, so first some convex optimization problems, some convex optimization problems this week professor has taught. So first problem was the beam forming optimization problem. Okay, so here we will take one single input and multiple output channel. So that is a CMO channel. Uh, so that means single input means one transmit antenna is there. So suppose this is the transmit antenna, uh, and there are many antennas for receiver. So these are the receive antennas, receiver side, and we are sending a signal X, and here there are L number of antennas. So we are observing L outputs at the receiver. So so for Y1 equal to what should be the case? So here this channel is there H1, H2, HL. So Y1 equal to H1X plus N1, Y2 equal to H2X plus N2, YL equal to HLX plus NL. Now combining these both L number of equations, we will get y1 vector, receipt vector y equal to h is also a vector hx plus n. So where this h is equal to h1, h2, hl, and n equal to n1, n2, nl. So this is the receipt vector we are getting. So now we'll do beam forming. Beam forming is done to recover this x vector properly. So that means we'll multiply something. So we'll beam forming is nothing but multiplication of a another vector with this y. So suppose after so we are doing beamforming so we are getting the signal r equal to some w hermitian sorry w transpose all are real we are taking so w transpose y plus so sorry w transpose y. So this is the y is the beam forming vector, sorry w is the beam forming vector, sorry y is the receipt vector and w is the beam forming vector. So 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 this is the scalar, r is the scalar, and okay, so ultimately we are getting w transpose into y equal to hx plus n. So this is equal to w transpose hx plus w transpose n. Okay. Uh, uh, okay. So now the optimization problem is that so this is the signal part, and this is the noise. So W transpose H we are taking as one unit. Okay, and our optimization problem is so optimization problem is we have to minimize this noise power. What is the noise power? Noise power is so this is a noise part. So this is taking we are taking as n tilde. Let's take n tilde. So so expectation noise power is equal to expectation of n tilde uh, n tilde transpose. Here the n tilde is a scalar, so everything will uh, okay. N tilde is equal to W transpose N and N. So this is the N transpose W. Okay. So then this is same as expectation of so W and so this W is not a, random vector. So we can take this outside. So expectation of N transpose then W. Okay, so this is W transpose. Expectation of N transpose is the sigma square I identity matrix, and then W. Sigma square is the noise power. Okay, so W so transpose W sigma square, that is can be written as sigma square norm of W square. Okay, so then minimizing this noise power, that means sigma square norm of W square with respect to W subject to this W transpose H is equal to 1. So this is the minimization problem or optimization problem. So we can also write down in this way also. Minimize W transpose W. This sigma square we can omit. This thing what is non-negative term. This then subject to scaling term. So W transpose H is equal to 1. So this is the optimization problem, convex optimization problem. Uh, Now how to solving? So we'll find out the Lagrangian. So the Lagrangian is uh, uh, 1 minus W transpose H. So this is the Lagrangian multiplier. In just derivative this with respect to W, that is equal to 2 into W plus sorry minus lambda H equal to 0. That is same as W is the optimal, that is equal to lambda by 2 H. Okay, so so this so now we have to find out what should be the lambda. So lambda, we need to put this optimal W star in this constant equation. Okay, in this equation. So that means W transpose H equal to 1. Uh, so that is same as lambda by 2 H transpose H. is equal to 1. So that means lambda equal to 2 by norm h square. Now put this lambda here in this equation. So we are getting W star is equal to sorry, H divided by norm of H square. The optimal W star. So that is the optimal beam former. So this is also called as MRC, maximal ratio combiner. So this is okay because as it maximizes the SNR. That means suppose we are getting this y1, y2, yl vectors. Okay, then we are multiplying this. The receiver were sorry y1, y2, yl multiplying with h1. Okay, h1 conjugate. I'm sorry, not h1. h1 by mod h1. Correct. So we're multiplying it with and this R is the decision rule actually. So not decision rule. So R will uh, be some statistics, sufficient statistics. So after we'll use R to determine X actually. X set. This will give X set. Okay. Now so now the second thing is that so this beam forming with interference. So for the beam forming with interference, so we have two transmit antennas. One is this is the desired antenna is the interfering. So this is the transmission side and this is the receiver side. Okay, this is the interfering signal xi and this is x is the desired signal. Okay, so now what should be the y receive vector? Y is equal to h. So from here to here is the h. From the desired antenna to the all the received antennas is the channel vector is h, and here to here it is the g. Let us take from the interfering antenna. So hx plus gxi plus n. So this is the uh, received signal. Now what will the R is equals to y transpose, sorry, W transpose y, and so this is the W is the beam forming vector or beam former. So so that is same as W transpose Hx plus W transpose Gxi plus W transpose N. Okay. So this is the signal part. This is the whole interference plus noise equal to n tilde later state. Okay, so what would be the expectation of n tilde and n tilde transpose? So one second. So this is not a scalar. So this is not a vector. It's a scalar. So this is same as equal to expectation of n tilde is equal to W transpose G xi plus W transpose N, and this transpose is G transpose W xi plus N transpose W. Okay, so this is the same as expectation of W transpose G xi G transpose W xi uh, plus plus W transpose N transpose W. Why? As only these two terms, so the cross terms will be zero because we are taking the expectation of xi and n is equal to zero. That means this signal and noise are uncorrelated. So this will be same as expect. So W is not a random, is a non-random vector. W transpose G is also non-random vector. Sorry, yeah, non-random vector. mm, G xi square. So G transpose xi square equal to sigma I square. Let us take plus W transpose sigma square W. So ultimately, they are giving. So this is same as W transpose sigma I square is G transpose plus sigma square W. Right, sorry, I. So this is the R. Okay, so that is equals to W transpose R W. So now the minimization problem is uh, optimization problem. problem is minimize this W transpose RW with respect to, so first subject to W transpose H equal to 1. So this thing is signal part. Okay, so W transpose H equal to 1. So the solution is same, just finding the Lagrangian and differentiating the Lagrangian and setting that to 0. So that will give the solution as this W star. Process is same, W star equal to lambda by 2 R inverse H. Okay, and putting this W star, this optimal W star in this constant equation, in this constant in this sorry, this constant equation. So this will also, so this will give um, this will give this lambda is equal to, lambda is equal to 2 by H transpose R inverse H. So that means this optimal beam formula is equal to R inverse H by divided by H transpose R inverse H. Okay, so this is the optimal beam format. Beam format, and then the third case is that three is the zero forcing. Zero forcing beam forming. So here we will force the interference term to 0. So that means so interference is forced to 0. Um, okay. So this y equal to hx plus gxi plus n. So then r is equal to w transpose y equal to w transpose h x plus w transpose g xi plus w transpose n. Okay, so now this so this is a signal part where we know w transpose h equal to 1, and this is the interference term. So here we will say this w transpose g equal to 0, then this noise will become 0, sorry, interference will become 0. That's why uh, so this is the zero forcing condition. Okay, then optimization problem will become, so we'll have this one constant and this second constant. Optimization problem will be only this a noise. So to reduce the or to minimize the noise power only, noise term. So optimization problem is minimizing the noise power. Noise power is, we know, we have calculated earlier. So it will be some sigma square, norm of W square. So sorry, minimize is sigma square norm of W square subject to these two constants. One is W transpose H equal to 1 and W transpose G equal to 0. So then This can be written similarly. We can write down minimization of W transpose W, and where it is subject to W transpose H equal to 1 and W transpose Z equal to 0. This is the so this is the optimization problem, constant optimization problem. So how to do that? Similarly, we will find out the Lagrangian. Okay, and this sorry. So these two constants can be written in a single constant alone. So that will be some. So first one is H transpose W equal to 1. Second one is G transpose W equal to 0. So then we can write down this 1 and 0. So this is H transpose and this is the G transpose and this is the W vector. Okay. So mm, okay. So this is can be written as some C transpose. So that means C transpose W is equal to this is some E1 vector. Okay. So where this C is equal to uh, uh, H and Z. Okay. H and G. So so these two constants can be so some C transpose W equal to E1. So here we will have some two Lagrangian multiplier. So Lagrangian is equals to W transpose W minus lambda. Lambda is a vector there as there are two terms only. So lambda is equal to lambda 1, lambda 2. Let us take. So lambda uh, transpose this E1 minus. Okay, so the E plus lambda transpose this E1 minus C transpose W. Then so finding the gradient of lambda, so L Lagrangian, and then putting that equal to 0. That will be same as this 2W uh, and minus this C. Okay, so this will be C, mm, C lambda 0. So then this W star equal to C lambda into half. So then put these things to in this equation. In this equation, then we will get uh, what is this C transpose W. So C transpose W is the C lambda is equal to E1. E1. Okay. So then this lambda is equal to 2E1 2E1 and this inverse. Okay, so that means C transpose C inverse E1 and then 2. Okay, so this is the lambda. Then putting this lambda value to W star. So W star will be so C into lambda. So C into lambda is the C transpose C inverse into E1 is the optimal beam formula. Then the fourth one and last beamforming is the robust beamforming. Robust means there are some so the first point is no sensitive information, no perfect channel state information at the receiver. Second one is there is channel estimation error. Okay, so that means this the optimization problem will be um, already professor has solved. So the ultimate optimization problem will be minimizing this W transpose R W subject to W transpose P norm. So there is an equal to W transpose HE. H is the channel estimation minus 1 scalar. Okay, so this is the optimization problem. The solution is W star will be minus lambda R plus lambda Q inverse into HE. So where this Q is equal to P transpose minus HE transpose. So this, I will not go through the whole process as professor has already done it. So now we'll go to some sample problems. The first one is so gradient of so first question is fx fx comma y is equal to x square by y, where is okay. Let us take z as a vector which has two components x and y. Then f of z is equal to x square by y. Now, what will be the Hessian of this f? So, find the Hessian. So, solution is that uh, del f del x equal to 2x by y. Then del f del y equal to minus x square by y square. Then del 2f del x del y that is equal to uh, x so minus 2x by y square, and del 2f del y del x is equal to with respect to y, so uh, minus 2x by y square, this is also same. Then del 2f del x2 that is equal to sorry yeah del x2 that is equal to 2 by y, and del 2f del y2 equal to minus, so this is a 2 mm, x square by y cube. So sorry, so the Hessian will be 2 by y minus 2x by y square, 2x square by y cube. So this is the same as 2 by y cube we can take as common. Okay. So it's y square and then minus xy x square same as 2 by y cube y minus x y minus x. Okay, you can check it y square minus yx minus xy minus x square. So this is a vector. Suppose this is a vector some uh, z prime, so z prime. So this is the 2 by y cube z prime to, oh sorry, let us take z1. So z1 transpose, correct. And as we are writing, so this is a positive definite matrix. Okay, because we can write down this as a z1 transpose for due to the structure for for y greater than equal to 0. So this for y greater than equal to 0. And so the second question is is f of z is convex. So the solution is yes, as this as is greater than equal to 0 for third one is f of x1 comma x2 is equal to x1 x2. So same question, find the Asia. So the solution is uh, so this so del x1 equal to x2, del x2 equal to x1, del 2f del x1 del x2 equal to x1 1, right? Sorry, 1 second. And del 2f del x1 x1, yeah, 1, and then del 2f del x1 2 that is equal to 0, and del 2f del x2 2 that is equal to 0. So now what's to the Asian? So this This is the 0, 0 and 1, 1. So it's the anti-diagonal matrix. It's okay. So let us find the eigenvalue. So what should be the eigenvalues? So determinant of minus lambda 1, 1 minus lambda is equal to 0. So lambda square minus lambda square minus 1 plus 1 equal to 0 equal to plus minus 1. So as the negative eigenvalues is also possible. So this is not a positive semi-definite matrix. Okay, so so F is okay. So it's not a sorry. So the next question is so the next question was is f of x1 comma x2 convex? The answer is so f of x1 comma x2 is neither convex nor concave. Now the second oh now the second now the next question is B here. So B here for AWGN additive void Gaussian noise channel uh, with SNR is equal to P by sigma square equal to gamma is is Q root gamma. Okay, so prove that. So how to prove it? So now the for the AWGN channel, y equal to x plus n, all are scalar. Okay, so this is the uh, so now we need to find out the x hat. What should be the x hat? Okay, so the ML detection rule will be so 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 y given x equal to plus root e. Here is the p. Okay, so that means this plus root p within real detection rule. So the how to okay now the p of y given x equal to plus root p is equal to 1 by pi sigma square exponential of minus y root p by sigma square, and this p of y given x equal to minus root p, that is equals to 1 by pi sigma square exponential of minus of mod of y plus root p by sigma square. So putting this to a PDF. in this detection rule. So mm, and taking the log also. Okay. So that means so putting the log of minus now this is the detection rule. Okay, now finding the error. So probability of error is equal to okay. So this is the now probability of error when x is equals to plus root p. That is equal to this probability of error is when this is less than equal to 0, less than 0 when x equal to plus root p. So that is equal to that is equal to q of root over this p by 2 sigma square. Okay, and so this is the this now. So probability of error is equal to half. So sorry, if you calculate this probability of error when x equal to minus root p, it will also come same. So probability of error equal to half into this q of plus half into the same thing is equal to q of root over p by 2 sigma square. This is the case for for complex channel. Now for real case, it will become equal to QOY root over P by sigma square. Now the next question is uh, okay. So the next question is fx equal to find the Asian. So fx equal to so some x1 dot 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 xi dot x n power 1 by n. So now del f del xi, let us find out. That is the 1 by n, 1 by n, and then this xn or 1 by n minus 1, and then this x1 dot 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 xn except xi, no xi. Okay, so now similarly, if I find out the del to f del x k del x l, sorry, del x I del x j is equal to n square. So what should the Asian should be minus. Okay, yeah. So and then this is less than equal to zero. You can check it. So this equal to zero. So this gives this uh fx concave function. Yeah. Okay. So then the second is that seven max of sorry, not max. Every norms is convex. That also maybe earlier I've told also. So this every norm norm of LP norm is equal to defined as mod of xi power p divided by 1 power pi equal to 1 to n, where this p greater than equal to 1. So this is the every norm is a convex function. And question number 8 is that max of x1 to dot xn. This is a convex function. Is also a convex function. Yeah. So this is the proof why this maximum is also convex function. That's all for today. So I can revise that first is convex optimization problem. Uh, okay, so four convex optimization problems professors has solved. One is beamforming optimization problem, normal beamforming, that is the single no interference is there. So here CMO channel we have taken one single input and multiple output channel, and so this is here there is no interference. Okay, so CMO channel we have taken. So for this case, the optimization problem is as shown here, minimizing W transpose W subject to W transpose H equal to 1. Then we find out the Lagrangian, then derivative of that Lagrangian will be 0. So that we have done here, and this is the optimal beamformer. And then second case, so this is also called as maximum ratio combiner. Uh, Beamforming with interference. For this case, we have two transmit antennas. One is desired antenna, another one is interfering antenna. So here we just need to maximize the minimize the total signal plus no inter sorry we need to minimize the noise plus interference term, the interference power. Mm, so, uh, so so that is this is the optimization problem. Okay, W transpose minimizing W transpose RW, where R is the covariance matrix of noise plus interference, and then the optimal beam formula is found out to be this R inverse H divided by H transpose R inverse H. And then zero forcing beam forming. So here we will forcing the interference term to be 0, and then we'll minimize the noise power. Okay, so here we'll have two constants. Earlier we have one objective function, or one objective function and two constants. Sorry, one constants. Okay, so earlier we have this is the one objective function and one constant. Here we have one objective function and two constants. So this is so, and um, we can merge these two constants in one constant using this another C vector, and this is a vectorized Lagrangian. So that means I mean this Lagrange multipliers lambda is not a scalar here. Here it's a vector. So. mm, so this is the optimal solution. And robust beamforming, for this case, we have channel estimation error, and we know that we need to minimize the this noise plus interference power, where this subject to this W transpose P less than equal. So this is coming from the ellipsoidal those estimation error scheme what professor has taught already. So that means so this breaking so this ellipse. So this is the channel estimation. H is the channel estimation, and there some was in some um, point this actual channel is situated. So from that ellipsoidal concept, here we are using that concept. So the solution is W star equal to this thing. Okay, so the whole derivation is there in the class. You can see. Uh, okay, so the sample, then I have taken some sample problems. So here it is x square by y. Suppose there is a function x square by y, where x and y are the two components of a vector. Then first through the Hessian. So Hessian is calculated as this, and this is the positive semi-definite matrix, and so the f of z is a convex function. And Then it's a convex function, and then the second case, second problem we have taken f of x equal to x1 x2, where x1 x2 are the two components of a vector, and then we need to find out the Hessian, as well as we need to say that is this fx is convex or not. So we are getting the Hessian as a anti-diagonal matrix, and the this this eigenvalues are plus minus 1. So as the eigenvalues are non-negative, I mean negative, so that's why it's not a positive semi-definite matrix. So hence it's neither convex or not concave function, because the one eigenvalue is positive, another one is negative. Sorry, one is one is this is the lambda. So one is positive 0, one is positive plus 1, another is negative. Okay, so if all are negative, then we can say it's a convex function. If all are positive, then we can say it's a convex function. But so here positive, negative both are there. So that's why it's neither convex nor concave. Okay, so then how to find out the beta rate for AWGN channel? The whole process is derived here. So actually, this is not necessary maybe, but yeah, for the sake of uh, proper derivation, so I've done here. So then the next question is this geometric multiple. So that okay. So geometric mean. So the second question is how to find out the Hessian for the function of geometric mean. So here this is the geometric mean actually. Okay, so this is the Hessian we are getting, and it's a concave function. So actually, these derivations I have done, but the second one del 2f del xi del xj that I didn't do here, but you can check it. This is coming like this only. So then we can write down in this way. So this is a concave function, and every norms in r power n is a convex function actually, and then max of some elements, max of all elements, max over all the elements in a vector is also a convex function. So the derivation is also here. So that's all for today. If you have any question, you can ask me. Sorry. Okay, let's stop here. Thank you for joining. Have a good weekend.